Download this code from codegive.com, link in the description below. Understanding the problem with UUIDs. UUID, Universally Unique Identifier, is a 128-bit number used to uniquely identify information in computer systems. While UUIDs are widely used due to their ability to provide a high degree of uniqueness, they do have some drawbacks that developers should be aware of. This tutorial will cover the issues surrounding UUIDs, their practical implications, and provide code examples to illustrate these points. Common problems with UUIDs. 1. Size and storage overhead. UUIDs are larger than traditional integer-based primary keys, example 4 or 8 bytes. A UUID takes up 16 bytes, 128 bits, which can lead to increased storage requirements, especially when used as primary keys in databases. 2. Performance issues. The larger size of UUIDs can lead to slower indexing and join operations in databases. They are less efficient in terms of CPU cache, which can slow down queries when working with large datasets. 3. Readability. UUIDs are not human readable and can be challenging to debug or manually inspect. They look like this: 550E8400E29B41D4A716446655440000, which is not intuitive. 4. Randomness and collisions. While UUIDs are designed to be unique, they can theoretically collide. This is extremely unlikely, especially with versions 1 and 4, but the possibility exists. 5. Lack of sequential order. UUIDs do not have an inherent order, which can lead to fragmentation in databases. This is particularly problematic in systems that rely on sequential IDs for performance reasons. Code example: generating and using UUIDs. Here's a Python example that demonstrates the generation of UUIDs and discusses their impact on performance when used as database keys. Installation. Make sure to have the UUID module, which is part of the Python standard library, so no installation is necessary. Python. Import UUID. Import time. Import SQLite3. Create a new SQLite database, or connect to existing. Con equals SQLite3.connect, example.db. C equals con.cursor. Create a table with UUID as primary key. C.execute. Create table if not exists users. ID text primary key. Name text not null. Def generate _UUID. Return str, uuid.uuid4. Insert multiple records. Def insert _records, number _records. Start _time equals time.time. For in range, number _records. User _ID equals generate _UUID. C.execute, insert into users, ID, name, values, user _ID, user. Con.commit. End _time equals time.time. Print, f inserted number _records in end _time, start _time .2 f seconds. Query performance. Def query all _records. Start _time equals time.time. C.execute, select asterisk from users. Records equals C.fetch all. End _time equals time.time. Print, f queried len, records in end _time, start _time .2 f seconds. Example usage. Insert _records, 1000. Query all _records. Close the connection. Con.close. Explanation of the code. 1. Database setup. We create a SQLite database and a table that uses a UUID as the primary key. 2. UUID generation. The generate_UUID function creates a new UUID using uuid.uuid4, which generates a random UUID. 3. Inserting records. The insert_records function inserts a specified number of records into the database, measuring the time taken to perform the operation. 4. Querying records. The query_all_records function fetches and counts all records from the database, again measuring the time taken. Conclusion. While UUIDs provide a convenient way to ensure uniqueness across distributed systems, their drawbacks in terms of storage size, performance, and readability should be carefully considered. In many applications, especially those with high transaction volumes or requiring efficient database operations, alternative methods, like auto-increment integers, might be more suitable. Always evaluate the specific needs of your application and the characteristics of your data before deciding to use UUIDs. Understanding UUIDs, problems and considerations. UUIDs, universally unique identifiers, also known as GUIDs, globally unique identifiers, are 128-bit numbers used to uniquely identify information in computer systems. They are widely used in databases, distributed systems, and applications where unique identification is essential. While UUIDs offer several advantages, they also come with some challenges and drawbacks. This tutorial will cover the primary problems associated with UUIDs, illustrated with code examples in Python. 1. Length and readability. Problem: UUIDs are long, 36 characters in string representation, which can make them cumbersome to handle, read, and communicate, especially in user interfaces or logs. Example: Python. Import UUID. Generate a UUID. my_UUID equals uuid.uuid4. Print, f generated UUID, my_UUID. Output: generated UUID, A3BB189E8BF9388899128ACE4E6543003. Solution: use a shorter identifier where possible, or encode UUIDs in a more compact form, example base 64. 2. Performance issues. Problem: UUIDs can lead to performance issues, particularly when used as primary keys in databases. Their random nature can lead to fragmentation and inefficient indexing. Example: Python. Import time. Import SQLite 3. Create a database and a table with UUID as primary key. Con equals SQLite3.connect, memory. C equals con.cursor. C.execute, create table items, ID text primary key, name text. Insert 1,000,000 entries. Start_time equals time.time. For underscore in range, 1_000_000. C.execute, insert into items, ID, name, values, str, uuid.uuid4, item. Con.commit. End_time equals time.time. Print, f insertion time, end_time, start_time seconds. Solution: consider using sequential UUIDs, example UUID v1 or UUID v6, or auto-incrementing integers if performance is critical. 3. Collision risk. Problem: although the probability of a UUID collision is extremely low, it is not zero. In scenarios where strict uniqueness is required, even a minuscule chance of a collision can be unacceptable. Example: Python. Function to simulate UUID collision. Def simulate _ collision. Scene equals set. For _ in range, 1 _ 000 _ 000. New _ UUID equals str, uuid.uuid4. If new _ UUID in scene. Print, F collision detected, new _ UUID. Return. Scene.add, new _ UUID. Print, no collision detected in 1 million UUIDs. Simulate _ collision. Solution, use a UUID generation library that implements collision detection or implement your own checks when necessary. 4. Complexity in merging data. Problem, when merging data from different sources that use UUIDs, ensuring uniqueness can be complex, especially if the same UUIDs are generated in different systems. Example: Python. Assume two systems generate UUIDs. System _ A equals str, uuid.uuid4, 4 _ in range, 3. System _ B equals str, uuid.uuid4, 4 _ in range, 3. Simulate merging data. Merged _ data equals system _ A plus system _ B. Print, merged UUIDs, merged _ data. In real-world applications, you'd have to check for duplicates. Solution, use a namespace or prefix for UUIDs generated in different systems to avoid clashes. 5. Incompatibility with certain systems. Problem, some older systems or protocols may not support UUIDs directly, requiring conversion to other formats. Example: Python. Converting UUID to a simpler format. Simple _ UUID equals str, uuid.uuid4, replace, dash. Print, F simple UUID, simple _ UUID. Output example, simple UUID, A3BB189E8BF938899128ACE4E65430003. Solution, ensure that your system is compatible with UUIDs or provide alternative representations. Conclusion: UUIDs are powerful and versatile identifiers that can simplify many aspects of data management and identification. However, they come with their own set of challenges, including length, performance, collision risks, merging complexity, and compatibility issues. Understanding these problems can help you make informed decisions about when and how to use UUIDs effectively in your applications. Always consider the specific needs and constraints of your system when deciding on an identifier strategy.